I will introduce you the webinar of today, which title is Dynamic Virtual Power Plant to Combine Flexibilities of Dispatchable and Non-Dispatchable Renewable Energy Sources, the POSYTYF project. This webinar is hosted by ISGAN. ISGAN is the International Smart Grid Action Network, an International Energy Agency technology collaboration program. ISGAN is also an initiative of the Clean Energy Ministerial, formally established in 2011. ISGAN creates a strategic platform to support high-level government attention and action for the accelerated development of smarter and cleaner electricity grids around the world. ISGAN currently consists of 27 contracting parties. Their nominated representatives form the executive committee headed by the presidium, assisted by 2 co-secretariats and the operating agents. ISGAN's vision is to accelerate progress on key aspects of smart grid policy, technology, and investment through voluntary participation by governments in projects and programs. ISGAN activities focus on 5 principal areas: policy standards and regulation, finance and business models, technology system development, workforce skills and knowledge, users and consumers engagement. ISGAN facilitates dynamic knowledge sharing, technical assistance, peer review, and, where appropriate, project coordination among its contracted parties. The ISGAN value proposition relies on conferences and workshops, policy and technology briefs, discussion and technical papers, casebooks, and webinars. Within ISGAN, the ISGAN Academy offers the ISGAN community means of rational and efficient continuous technical skill complement and update in the fields of smart grids. The Academy is proposed as a set of e-learning and reading core modules dealing with the entire value chain of smart grids. Webinars organized or co-hosted with the Clean Energy Solutions Center. The webinar of today is entitled Dynamic Virtual Power Plant to Combine Flexibilities of Dispatchable and Non-Dispatchable Renewable Energy Sources, the POSYTYF project. This webinar introduced the concept of Dynamic Virtual Power Plant that is under development by the European Commission funded project POSYTYF. DVPP aims to facilitate renewable energy sources integration into the electrical network. After an overall project presentation, the webinar will introduce the dynamic virtual power plant concept and the definition and specification of the relevant scenarios. The speakers are Bogdan Marinescu, professor at the École Centrale Nantes and coordinator of the POSYTYF project, Oriol Gomis Belmund, professor at CITSEA, Universidad Politécnica de Catalunya, and Carlos Collados Rodriguez, PhD student at CITSEA, Universidad Politécnica de Catalunya. Please use the question and answer tool to pose your questions. The speakers will answer at the end of the presentation. The recording of this webinar will be available on the ISGAN YouTube channel. Now, I leave the floor to the panelists. Please enjoy the webinar and the roundtable that will follow. So I will leave now the floor to Bogdan. Please, Professor Marinescu, the floor is yours.
Thank you, Matteo. Thank you, Chairman, for this introduction. Hello, good afternoon to everybody. So I will start this presentation, of which the agenda is this one. So I will first I'll give you an overview of the POSYTYF project. And I will focus on definition of the new concept that we developed in this project at all levels, so the DVPP concept. And after that, the seminar will focus on contributions from the first work package, which is generally about the definition of the scenarios and the study cases from the DVPP. Okay. So first, just to give you some hints about POSYTYF projects. So POSYTYF comes from precisely powering system flexibility in the future through renewable energy sources. So it's a response to the European Commission call, a general call on development of solutions based on renewable sources that provide flexibility to the energy system. So it's a project, it's a research and innovation actions for 3.5 year duration. So we are now almost in the middle of the project. So it will last till November, the end of 2023 year. Coordinator is École Centrale of Nantes in my person. And the general context so is to address, so of course the target is to facilitate integration of renewable energy sources in general, and we focused on stability issues at several levels, as we consider that at this stage, stability is one of the main bottlenecks to further development of such penetration of renewable energy sources. So we are tackling these on many aspects of stability, the classical ones. So I mean that all we know, the voltage stability, synchronization items and things like that, but also from new perspectives of investigating new notions of stability, which are related to massive integration of power electronics. So one part of the project is to focus on that and to enlarge this framework, these definitions and assessments of stability in modern power systems. So this is the general target and kernel point, and after that, a more practical one is to make a zoom on what we call distributed renewable energy sources. So to consider different sources, different nature of sources, especially distributed on the grid, and to try to aggregate them and coordinate them from the point of view of control and operation, to have more flexibility for grid integration and contribution to system stability and ancillary services in a more general sense. So we are dealing with notions of dispatchable and non-dispatchable RES. Dispatchable, non-dispatchable means that can face variation of resources. For example, we no longer have sun or wind as part of the grid when we have some RES connected, but we can increase production of other RES connecting further away a little, but belonging to the same concept of virtual power plant that we try to develop to have such optimal operation and to try to behave as much as possible as a classic generator. We can be permanently connected to the grid and to provide the energy and services. And this has to be an alternative to electrochemical storage. So to try to do this with this mixed portfolio between dispatchable and non-dispatchable, to have an alternative solution to massive integration of storage to face this volatility of RES. So this is the general context. And a word about the organizations of the consortium. So we have a very rich consortium. So we have 11 partners. And what is very important and the power of this consortium, I think, is the combined expertise on several things, several areas of expertise. So we match at least 4 of them in this work in POSYTYF project: power system, general power system expertise, power electronics, automatic control, and specificity of renewable energy sources, this kind of generators. We have also a good mix between academic partners and industrial partners. So we have 5 universities and 1 research center and 4 industrial partners on key competencies on transmission, distribution, generators for renewables, and software producers. The organization, so we have classic organization with some administrative packages on the right. So package 6 and 7 for management and dissemination of results. And at the technical level are the green packages on the left. So we have one, package 1 is for scenario definition, DVPP definition in large. And today's seminar is devoted to their work. First part of the results, of course. And we have after that 3 packages concerned with control. These are package 2, package 3, and package 4. And we should work here at the different levels. For example, package 2 is more oriented to unit level, to controls of generators. Package 3 and 4 more related to grid or system level for high-level controls like secondary controls and ancillary services. And a very important package, package 5, is devoted to optimization of the DVPP in general for operation and configuration. And this, the task, main task of this package is to propose competitive solutions, especially against electrochemical storage, and to see which are the best definitions and configurations of DVPP for that. Okay, so after this general presentation, some more details about scientific and technical issues. So, as I said, the general target, the global target of the project is to enable participation of renewable energy sources to ancillary services in the general way. But more specifically, we have some kernel points here from the scientific point of view to solve, to advance on that. So first one I will mention is to manage specificities of decreasing global inertia of the system. So this is to face this lack of inertia due to increasing power electronics connected sources to the grid. I mentioned already problems about stability definition and assessments, but there are also many other problems from the control point of view, from the analysis in general. So if you want to track interactions, oscillations, and things like that, and we are thinking to new tools and methodologies to deal with that. Another point is very important is to deal with this coordination between different sources. So our virtual power plant is built from, as you will see just after that, the technical details of these presentations from my colleagues from Barcelona. We pack together many different kinds of sources. And we want to reach an optimal level of coordinations and coordination of this. And on one side for optimality is coordination, on other sides we are running, we are trying to push solution also on in the decentralization way, is just to reach some flexibility in operation of the DVPP and some resilience. So for example, if some renewable energy sources of the DVPP are shut down for different reasons, so to be able to run with the others with the same grid services and the same production, of course, for the overall VPP. The robustness is also an important item here in the general sense, and in the particular sense of disturbance rejections, which are many, because we are trying to deal with a large perimeter to look for both connections at transmission and distribution level. And this is a specific point of our concept of DVPP. We consider DVPP on both levels, And maybe the last point I will mention, it's about optimization. And also this is a specific point of view of our work. We tackle both static and dynamic points of view in this optimization. So usually in classic VPP, the one that existed today, most of them are related to the static optimization. So we are looking in this DVPP to production of active power, connection to markets for eventually, but very few DCP concepts are merging these static objectives to dynamic ones like control, participation to ancillary services for the grid. So these are our main concerns here. And to analyze and to propose solution for that, we are now developing what we call the DVPP concept, so dynamic virtual power plant concept, with against the classic virtual power plant concept. So this is well, technically a set of generators, so fresh generators, of course, but what is important is the way we try to run them to do a good mix between dispatchable and non-dispatchable portfolio. This is one point. And the other important point is to provide these ancillary services to the system. So I put here on this slide a conceptual example of our DVPP. So it's a set of machines put here in red. For example, we have PV here. We have some wind, the W are wind, S it's storage, for example. And there are some important specificities. Some of them I already mentioned, but I will maybe better explain on this figure. So first of all, and this is a new point, I think, for this DVP concept. So we consider multiple grid connections. So these points are listed here on the right. So this means that the DVPP is not a specific region of the grid where are some renewable concentrated there. So it's the opposite of that. So we consider a set of renewable, but that can be installed connected to the grid in no specific locations. For example, here, there are some here on the transmission grid. The other ones are on the distribution grid. And we can have even several distribution grids, like in this figure, we have 2 distribution grids, and the DVPP is the collection of all these red generators, which are in fact on 2 distribution grids and 1 transmission grid. So we are trying to run this as a whole. So the DVPP will be a concept grouping these and should run in a coordination and to integrate them also to the existing ancillary service in general, in particular secondary regulation. And this is also a new point, an original point that we want to solve in this project: participation of such renewable energy sources grouped into in a unitary concept like the DVPP we propose, participation to ancillary to secondary services like voltage and frequency, the actual ones. Another important point, so in this quite general structure, is the imbricated, what I call here imbricated structure. So means, as I mentioned, the rest we consider are not grouped together and apart from the rest of the grid. They are imbricated with non-participating machine. For example, here, generator G2, it's a classic generator, which does not belong to the DVPP, but W1 is just close to this one and belong to the DVPP. And on the opposite, we have W8 and 9 and all these wind farm is far away from W1, but they belong to the same DVPP. So there is no specific relation in geographic vicinity or things like that, and no hypothesis to limit these to transmission onto distribution grid. So we try to tackle as general as possible from this point of view, this concept of DVPP. So this brings some problems, important things to solve, like dynamic interactions, because in this imbricated structure, we have strong dynamics interaction, not only between machines of the DVPP. This is quite easy to tackle because we will build the regulations for that, but there are also interactions between the machines, the generators of a DVPP, and the other neighbor generators like G2 or G3, which are closed geographically and electrically, but they are not in the DVPP. So this is an important point that we were trying now to solve via control methods, robust controls and and resilient controls. I talk about participation to secondary regulations. It's this is new, I think. It's original for our concept, but we target a full, what we call here a full participation. So it's not only some impact, positive impact, for example, for voltage support, but it's to be integrated into existing scheme of secondary voltage control, for example, or secondary frequency control as a standard generator, like a thermal generator, a classic thermal or nuclear plant, and to have this kind of participation from the technical point of view and also from the market point of view. And least but not last, an important point is the future scenarios. So as I mentioned already, for stability, we target also challenges brought by massive power electronics in these kind of grids. And in fact, in the project, we run in parallel two scenarios. So one scenario is a DVPP, which can be integrated in what we call actual operation scheme. So means the markets, the regulation, the secondary regulation as they are today. Okay. And the second scenario is what we usually call here in power system in general is 100% power electronics. So means to envisage the DVPPs that will work in a future grid in which, okay, it will be maybe not 100%, but power electronics connected devices will be the majority, and very few classic generators, thermal generator like this. Okay, so this is in few words the project and the DVP concept that we are developing. So I will give now the floor to my colleagues from package one to detail these DVPP configurations and scenarios as first results of their work.
Okay, thank you very much, Bogdan, for the introduction and the presentation. Now, as you said, we will introduce the general activities of the first work package of the project, and then we will also present the results which are included in the deliverable and which show the work we have been doing on the scenarios definition. If you can go to the next slide, please. Basically, in the first work package, we are addressing the definition of the scenarios, the general modeling of the system, and also the definition of specifications for renewable energy-based systems, where this dynamic virtual power plant, which Professor Marinescu was introducing, will be installed. First, we look at the conceptual definition of the scenarios in the first task. And basically here we consider basically different situations we have in Europe, different geographical considerations, different kind of resources available when it comes to renewable generation. And we sketch some conceptual diagrams which could represent a wide variety of systems, of scenarios which could be relevant in Europe. these scenarios, you will see that they are including some islands, also some interconnections and some systems in continental Europe, and also both in the south and the north, in some scenarios where there is a dominance of wind, in others perhaps it's more hydro, others perhaps it's more related to solar. And as I said, we are trying to capture a variety of relevant scenarios. Then in the second task, we are putting some numbers in some selected scenarios. Basically, what we are doing here is to start from the current situation in some example scenarios in Europe. What we are doing is not a detailed planning of the expansion of the system and how the renewables will be integrated in detail in a specific location. It is more a kind of a realistic analysis, trying to be realistic using some realistic numbers, but not using exact details of the systems we are considering. And in this case, basically what we are doing is to do an optimization on how we should deploy renewables in order to arrive to a given target in terms of penetration of renewables in the system, and see how the system could be evolving to arrive to this target. My colleague Carlos will explain later the details on how we are doing this, but basically what we want to understand in this second task, it is how the mix in the energy system will look like when trying to achieve different targets. And what we are seeing, it is interesting because if the target is like 50-60% of renewables, normally we are obtaining a mix based on solar PV and wind. But if we are aiming to higher penetration of renewables, aiming at, for example, 90% or 95 or 100%, then we see that the renewables which can provide an additional flexibility to the system are also gaining some value, because during some hours where there is a limited resource, the flexibility that these units can provide, it is gaining value compared to the others. These two tasks, as I said, are related to the definition of the scenarios. So basically what we are doing it is to define the scenarios both conceptually and numerically, and then use these scenarios for further other tasks in this work package and also in other work packages. These initial tasks are not providing details on the models, on the electrical networks, on the converters used, on the renewable sources used. It is more a general approach. These details are given in further tasks. Then in the tasks 1.3 and 1.4, what we are doing, it is working more on the specifications. We know that in the current power system, we have already a significant penetration of renewables, and this penetration, it is going to start more and more in the next years. So what we are doing here, it is to define the requirements we have nowadays based on existing grid codes, to summarize them and to think how the dynamic virtual power plants could address these requirements. And also we are looking at future scenarios, as Professor Marinesco was expressing in the previous part of the presentation. We are looking at these futuristic scenarios, and we are trying to understand what kind of requirements would be needed to deal with such systems. For example, if we envision a system with a very high penetration of power electronics, which can be 90% perhaps in some cases, or even 100%, probably then we need to look differently at the requirements in the system, and perhaps we need to come up with new requirements. This is the exercise we are doing in these tasks in 1.3, and also in 1.4 we are also thinking how this role of grid forming needs to be allocated in future power systems. If we have a significant reduction of the number of synchronous generation units and we have more and more power converters, we know that the power converters need to take responsibility on forming the grid in the network. This role assignment task, basically it is oriented to decide which converters in the grid need to take this responsibility. What's the best decision? And eventually this can come as a requirement for future power plants connecting to future networks. And finally, in the last two tasks, we are addressing the modeling to prepare models for the whole project. So basically, based on the scenarios we have defined, we are developing some models of power systems, trying to, as I said before, trying to be realistic, but perhaps not extremely detailed. Okay, so trying to provide some models which can be useful for different studies. And these models are prepared to be conducted using different simulation approaches, like electromagnetic transient simulation and also phasor simulation. and also including, in some cases, some switching models for the power converters. So we are considering different approaches, and we are providing models which can be used for our colleagues who are designing the control systems for the dynamic virtual power plants. This is implemented in the task 1.5, using some models in MATLAB Simulink, also using some open source approaches like Modelica to develop some of the models. And finally, in the task 1.6, what we are doing is to work together with the phasor simulation and the electromagnetic transient simulation to simulate large systems, also keeping some reasonable detail on some key elements like the power converters. So in this final task, we are trying to combine these two worlds of EMT and phasor simulation to provide relevant results of the two systems together. What we are presenting today, it is especially the outcome of the first two tasks. So it is related to the scenario definition, but probably in future deliverables and future communications of the project, we will also share some results on the other tasks. So, well, I just wanted to provide an initial introduction on the work package we are coordinating at UPC, and now I will let my colleague Carlos Collados present specifically the results achieved in these initial tasks. Thank you very much.
Thank you, Rob, for the presentation. My name is Carlos Collados, as you all said. I'm from UPC, Universidad Politécnica de Catalunya, and I will present the results we have already from these two first tasks, okay? So just to introduce the objectives of these two tasks that Oriol has already introduced, but just to be more specific, they deal with the scenario definition that will be used in future work in other work packages that are more regarding on the control design or economical optimization on different aspects that can be applied to virtual power plants. So these scenarios will, this task will define or have already defined the scenarios that these other work packages will work on. Okay, so these scenarios consider different criteria to be, let's say, defined. So we consider different topologies in the sense we have different system topologies like isolated system or synchronously connected, so AC connected system, or non-synchronously connected, so DC connected system. We have also considered different renewable technologies, both, let's say, controllable or non-controllable, also based converter-based technologies like the PV power plants or wind power plants, or also synchronous generation-based renewable energy, like could be geothermal or solar thermal or biomass. So we have different renewable technologies possible. But the idea is to go from a limited penetration of these renewables to a fully dominated system by this renewable energy. Okay, and as I said, this can be power electronic based, or they can be synchronous generation based. So another criteria to define this scenario is to have a transmission network, only transmission network, or also include the distribution level to some scenarios. So this would be the criteria to generate, let's say, the initial scenarios or the qualitative way to generate the scenarios. And then the second task aims to provide some numbers, let's say, to these initial scenarios and quantify the elements that are present on this system, like the installed capacity of every power plant, the line capacity of the single line, and so on. And this will be based on an economic and production data analysis. Let's say we have done an optimization approach. So let's start with some with a background and some definitions. So let's start with some numbers. We have seen in the recent years a huge increase of renewables. For example, we see here the target of the European Union for 2030 that they want to achieve at least 32% of renewable energy. In specifically, in case, for example, two countries, France want to arrive to 40% of the total electricity consumption, while Germany wants to arrive to 65%. And here we see different targets for different countries. For example, Spain sponsorized to 74%. Sweden is even higher than 80. So here we can see different and very ambitious shares of renewables in the future, in the near future for Europe. And well, so which are the main technologies we have considered for or to take part in these virtual power plants? We have considered only renewables. So for example, we can, regarding solar energy, we can find both photovoltaic based on converters, as I said, and both solar thermal. We see here some sketches of both technologies, but also wind energy, both onshore and offshore wind. But also, let's say, synchronous or more, let's say, conventional synchronous generation-based technologies like hydropower, biomass, or geothermal. In this particular project, we are not considering electrochemical storage, because what we want to do is how can we avoid this electrochemical storage by a good combination or a good control of all this renewable energy. So trying to be smarter, let's say, to avoid this installation of the electrochemical storage. And just to analyze the different characteristics of these technologies, or what is the advantages of or limitations of each of these technologies, we have analyzed different characteristics. For example, technical characteristics like controllability, dispatchability, the response time when they have to follow change of power, and if they present storage time and how much is this storage, okay? And also some economical characteristics and some, let's say, ecological or pollution characteristics. Okay, so let's start with controllability. The controllability is related to the capability to store the resource. So we find different levels for this characteristic. So the first one would be the non-storage capability. So a particular technology cannot storage the resource. So the maximum power injection of this power plant is defined by the resource. So the power injection can only be curtailed. This could be the case, for example, of PV and wind, where we see clearly that the resource gives you the maximum power available. Then we find other technologies that present limited storage of what we call converted energy. So this is the case, for example, the solar thermal power plants. If they present, for example, a molten salt tanks or some kind of storage system, but in a thermal energy store, let's say. And then we find the primary energy storage, so the storage of the fuel itself. So it would be, for example, low capacity. If we consider, for example, hydro, both pumping hydro or let's say the river hydro, that eventually these power plants could suffer from the lack of resource, for example, rain, or there is no enough flow from the river, or any kind of lack of resource. Then we find, let's say, we have called medium capacity. So nowadays we have include this biomass into this level, as we think that the resource of biomass is less than, for example, other resources like coal, gas, or uranium, or whatever. That we assume that at least now, maybe in the future this can change, that let's say the flow or the availability of these resources is now, let's say, infinite, or enough to deliver the generation. Okay. So then we go to dispatchability, that this characteristic is related to how the resource affect to the operation set point of the power plant. So for example, we see that again, we have 5 different levels. So level 1 would be that the resource always constrains the power output capability. For example, as I said before, the PV is totally restricted by the maximum power that the PV can deliver is totally restricted by the resource. It cannot be, let's say, higher than the resource at any moment. For example, if we go to level 2, we see that this power, this instantaneous power, can exceed the resource during a short period of time, during some seconds. For example, in wind, if we consider that we can extract some energy, some power from the inertia of the blades, we can say that, well, this dispatchability is higher, or it's better than compared to this photovoltaic power plant. Okay. Then we move to level 3. Okay, we say that the power output depends on the resource, but it can also increase by a secondary, let's say, energy source. That this could be the case, for example, the solar thermal. That you have, of course, the solar irradiation, that is the resource, but we have also the thermal storage tanks that even if we don't have a solar resource, we can or they can deliver some power to the grid even at night. So we have considered this is a 3. And then level 4 is the output power don't present any constraint, so they can go for example from 0 PU to 1 PU, so they can deliver all the power at any moment. And level 5, that would be the capability of power reversal. For example, pumping hydro, they can go from, let's say, from -1 in PU, so they are pumping the water to the upper reservoir, to the let's say generating 1 PU that they are turbining water down. Okay, so this would be our classification for this dispatchability. Okay, so regarding other characteristics like response time or fuel cost and emissions, we see here, well, from these two, let's say from these first two characteristics, we see that renewables present, let's say, a lot of challenges in terms of controllability and dispatchability. That's why we are working on this in power plant. But they present other advantages regarding, for example, economic reasons, no, cost of operation, or also related to emissions. And also response times, as we have some converter-based generation, they can provide also faster responses. Okay, you can find these two tables of characteristics, both technical and economical and emissions characteristics, in the deliverable 1.1 that will be uploaded in this link. I think it is not available yet, but it will be in the future with all the details of these tables. Okay. So let's move to the scenario definitions that is related to, let's say, the qualitative definition of the scenarios. Okay, as I said before, we consider different criteria to define these different scenarios. For example, the grid configuration, as we said before, we can find 3 different configurations: that is isolated, is interconnected, and disinterconnected. We have the possibility to include also a distribution grid or no. We have also the option to include conventional generation or just include renewable generation, and we have the option to include a storage, always considering non-electrochemical storage or no. So combining all these different criteria leads to 24, let's say, preliminary scenarios, where for example, we can find isolated, where we can choose between distribution or not, where we can find we can include conventional generation or not, and we can choose between storage or not. So this gives us 24 different scenarios. Just to show an example, for example, this scenario 11, it is interconnected. Okay, this scenario 11 is interconnected. So we see here 2 different, for example, AC networks. It presents some distribution network. Okay, say yes. So we have here different 2 different levels. So let's say transmission network and the distribution network, and no conventional generation. We don't have any let's say thermal power plant, and it presents a storage that we do not define which is the nature of this storage. Okay, so we have 24 different scenarios, let's say generic scenarios, which are not size, so they are just, let's say, a qualitative scenario that can be obtained following these criteria. So to have an idea if these scenarios are relevant or not, what we did is to identify real locations where these virtual power plants can be spied on. Okay, so based on these three different scenarios, type 1 isolated, type 2 is interconnected, and type 3 is interconnected, we have tried to find locations, in our case in Europe, where these scenarios are relevant. One let's say restriction we had during the search was to find locations where the renewable resources was currently or potentially available. So even if there is not so many power plants installed, at least that they present renewable resources. As an example, we have many different in the deliverable, but as an example, we found Gran Canaria as isolated system. There is interconnected system. We saw, for example, Central West France, where there are many hydropower plants, some wind power plants, also PV power plants. So that's as an example. And as this is interconnected power system, we found the Balearic Islands, also in Spain, that is connected to the mainland to an HVDC link. Okay, so this could be a system connected to DC, interconnected through a DC system to the other network. So the idea is now, well, based on these 24 scenarios and based on these real scenarios that we have found, the idea was to select some scenarios, some realistic scenarios, not real, so realistic because we don't want to depend on, let's say, real data, but just to represent the different scenarios. So we defined 4 different scenarios related to these 3 types. We'll see. For example, this type 1 isolated, we have seen that they are related to small islands, for example, Gran Canaria, that they present simple system compared to continental scenarios. So in this case, we have represent these islands or these isolated systems with 7 bases. Okay, we see here 7 bases and 1 single voltage level as they are, let's say, simple systems. Regarding edge interconnected system, we have found, let's say, many different cases because most of the systems are edge interconnected systems. For example, we can find many different networks in Europe. So they are typically bigger than this type 1 and more mesh. So we have increased this number of bases from 7 to 13. You see here that there are 13 bases, and they present both transmission and distribution levels. In this case, we have defined 2 different scenarios because we have considered that in Northern Europe we can find more hydro and wind, also offshore wind, while in Southern Europe we can find maybe more PV, and also maybe we can find solar thermal, as the solar resource may be higher than in Northern Europe. And finally, as this interconnected system, they correspond, as we have seen, to bigger islands. So, for example, the Balearic system. So we have considered that they have a slightly more complex network compared to type 1. So we have represented it as a 11 bus network, okay, as we see here. And we see here that it is connected to the mainland, or to the AC network, to an HVDC link. While we represent, well, a different kind of technologies. These technologies, as I said before, are just like, let's say, or the distribution or the here are just qualitative. We have located them as in a qualitative way, but the idea in the task 1.2 is to size how much or how big should these power plants be in order to provide, let's say, the best solution in terms of economical characteristics. Okay, so the idea now is to size this scenario, so to provide specific numbers for every technology and every power plant. And how did we do this? So we use an optimization, which objective was the generation cost. So the idea was to minimize the total generation cost, including both capex and opex. Regarding the conventional generation, we consider that they were already installed. For example, coal, natural gas, or nuclear, and so on. They are already installed. So we only need the opex because they are already installed. and also the installed capacity that is already in the system. Okay, regarding the renewable generation, we will need the available resource, the OPEX, but also the CAPEX. If we consider that there is a part of this renewable generation, instead of CAPEX, we will need the installed capacity. And other things that, or other inputs that require this optimization is the total demand of the system at the minimum share of the renewables that at the end would, is the objective that we want to meet. No, we want to arrive to a minimum share of renewables while minimizing this total generation cost. In this first round, we have not included the constraints of the grid, the restriction of the grid. We have been working after the, let's say, the submission of the deliverable. We have some results, but I will not present it today. And the outputs of this optimization are the installed capacity of every renewable technology in global. So for wind, for every technology, we will receive, let's say, installed capacity, but not the particular power plant present in the system, because we have not considered the grid. And also the instantaneous generation for every technology. Now we have considered, let's say, a time resolution of 1 hour. So we see here, for example, we will see later more results. So we will see the generation for every hour. And regarding the constraints, we have considered, for example, for the generation that the generated power at every time is instantaneous generation must to be lower than the capacity of, or in the case that for example, for renewables, also the resource. Power ramping limit in case of it applies, but in our case, this is only, 1 hour resolution. We don't need this power ramping, but in case of having more resolution, I don't know, 1 minute, 2 minutes, or whatever the resolution could be, this power ramping may be relevant. For the storage, we have included the energy balance and also the maximum stored capacity of the system. And as system constraints, we have also included the generation demand balance. So the demand must match the generation, and a minimum share of renewable generation that at the end is the goal we want to meet according to the policies or whatever we want. So, okay, we have applied this optimization to the different scenarios. For example, this type 1, and we have not considered any kind of storage. So the only technology we have considered are PV and wind, as we see here. The demand and the resource data are based on Tenerife in 2019. So the maximum demand, is around 550 megawatts, and the minimum share of renewables is 74, because it is Spain's goal for 2030. So we have found that for this specific scenario, the installed capacity needed of wind and PV is the one that we see here. So to meet the 74% of the renewable energy, that is the summation of 31 plus 43, we need a 30% of PV, so in total almost 600 megawatts, and 40% of wind, that in this case almost 800 megawatts. And we have split this to technologies between two different power plants here. So we have here the system that we defined before for the isolated system with 7 buses, where we have placed this, let's say, these two technologies around these different buses. Okay, so looking at more details of the results, for example, we see here the daily generation. As we are, let's say, in a relatively low latitude, the solar production is almost constant during the year. If we go for lower latitudes, this will be different from summer to winter. And we see here the variability of the wind power plant. For example, we see here that some days are completely provided by renewable energy, while other days require more, in this case, thermal power plant delivered in gray here. Here we see hourly generation in January and August. We see clearly different, let's say, performance for the different months. Okay, and what happened if instead of considering only one minimum share, we studied the evolution of this installed capacity depending on the minimum share we need. No, so for example, we see here that we move from 0 renewables to 100% based system. So we see at the beginning the optimization starts installing only PV power plant, PV generation, because it is the cheapest option to meet the goals. And once the share is increasing, it uses also wind generation. And at some point, for very high renewable shares, this curve is exponential. And we see here, we cut here the axis, but we see here that for very high shares, we need a very high amount of, in this case, wind energy. So up to 12 gigawatts for 99% of renewables. So to meet 550 megawatts demand, we would need a 12 gigawatts, or well, 12 plus 2, let's say. So 14 gigawatts of installed capacity. So this, of course, makes no sense. So additional flexibility for the system is needed to avoid this cost increase, because at the end, all this installed capacity at the end is an increase of cost. So the idea is to introduce an element with some kind of storage. In our case, we have introduced a solar thermal power plant, which have an inherent storage capacity of 8 hours. And this can provide some flexibility. So if we look at the same graph than before, we see that for the first, for low shares of renewables, for example, up to 70%, this thermal power plant is not present in the system, so the optimization does not locate any solar thermal power plant. But as we increase this share, for example, 80%, 90%, the optimization starts using or starts installing this solar thermal power plant, because it can provide some flexibility to the system. We can reduce from, I don't know, 40 gigawatts before to around 5, or so a significant reduction. And if we compare the cost reduction, if we consider this case 2 as the base, we see that for very high shares of renewables, we can even divide per 4 this cost of generation. So this solar thermal power plant can lead to a reduction of the generation cost for very high penetration of renewables. So these power plants can play a role for very high, let's say from the optimal of the economical point of view, they are very useful for the final range of the renewable share. So if we look at particular results, the installed capacity, for example, for a share of 90%, we see here that the solar thermal power plant must have the 40% of the total capacity, and it can deliver 26% of the total generation. And here we have the scenario that we have already defined for the different technologies. And here we see that even during the day, for example, here we have the PV generation, and the solar thermal can also provide some generation during the night to be combined, for example, with the wind. Here we see a particular graph about the performance of the solar thermal power plant. So during the day, it starts storing the thermal energy, and okay, it delivers the electrical power whenever the system needs it. So we move to scenario 3. So this is a type 2 system, so an asynchronous system, and specifically the Northern Europe. So the particular resource data are from Netherlands in 2019. This demand has been scaled to have a maximum demand of 5,000 megawatts, and again, the minimum share of renewables is set to 74%. We have considered an installed capacity of pumping hydro of 1,000 megawatts, so a 5% of the total capacity that provides already, let's say, some kind of flexibility to the system. So we see here that to meet this 74%, we need 42% of wind, 31% of PV, and this 5% that was already installed from hydrogen. And here we see the specific daily generation for every technology. In this case, we see a difference between the performance of the PV power plant. In the case before in Tenerife, we saw that the performance was pretty similar during the whole year. In this case, we see clearly that in summer they are delivering much more power than in winter. Okay, and here we see an hour generation where we can see that the pumping works only, or the pumping only works when there is enough generation from renewable energy, and when there is not enough, here, for example, it combines with thermal to provide more power. Okay, and just to finish the presentation and give you some conclusion. So the conclusion of this deliverable was to provide some realistic scenarios for the future analysis of peak power plants for the future of all the other work packages. They are inspired in real data of consumption and real resources, but they are not real systems. We call them, let's say, realistic system, and we have defined, or we have sized them based on a cost optimization methodology. And we have considered different technologies to meet the specific requirements, arriving up to 100% of renewables. So we see that solar PV and wind can provide what we call the renewable backbone, so the main structure, but they have a lack of flexibility. So for the last range of integration, we need also solar thermal or pumping hydro, or some other technology that present some storage to provide some flexibility to the system. And we have seen that they are too expensive for low penetration, so the optimization only install it for the last range of integration. And this is all from my part. Thank you very much for attending. If you have any questions.
Thank you, Carlos. Thank you, Oriol, and thank you, Bogdan, for your interesting presentation. Now it's time to move to the roundtable, and so you have now the chance to